Hi, AP Calculus. We're doing 3-4 differentiation of inverse trig functions. And before I give you all of these derivatives right here, I'm actually going to skip and talk to you about a problem. We're going to kind of prove the things we're about to do. So this is maybe, you might have space to do it on your page, otherwise maybe just like watch and listen. So let's say we have y is equal to sine inverse of x. And I want to find this derivative. Well, the issue here is that I don't know what the derivative of sine inverse is. So instead of doing this with sine inverse, what if I take sine of both sides? And in doing so, I would get sine of y is equal to x, right? In a function and its inverse cancel each other out. So here's what I've got. And now I can take the derivative of this. The only issue is we do need to do a little bit of implicit differentiation, right? If I differentiate from left to right, the derivative of sine, if you sin, there's a consequence, but then I have to multiply it by dy dx is equal to the derivative of x is 1. So then we solve for dy dx. The derivative is equal to 1 over cosine of y. But this isn't really that good, right? We always want it to be in terms of x. So now we have to go back up to the beginning and consider this function right here. Y is equal to sine inverse of x. And this is another place where we're going to look at something you guys did in pre-calculus, which is kind of cool. So if I think about this function, y is equal to sine inverse of x, and I consider the inverse sine of y is equal to x. Well, let's look at what this looks like in a right triangle. Sorry, that was not super good, but you guys can forgive me, right? So let's say y is this angle, right? If I know sine of y is equal to x, SOHCAHTOA helps us remember that sine is opposite over hypotenuse. That means the opposite side here would be x, and the hypotenuse is 1. And now let's solve for this third side. So x squared plus, we don't know what this is, we'll call it a squared is equal to 1 squared. Solve for a squared is equal to 1 minus x squared, or a is equal to the square root of 1 minus x squared. So that's this side right here. The square root of 1 minus x squared. We have this triangle then that we're dealing with when we want to find cosine of y. And now again, we're going to consider SOHCAHTOA. Cosine is adjacent over hypotenuse. If this is y, here's our adjacent over the hypotenuse of 1. So we can really write dy dx as 1 over, remember, adjacent, which is the square root of 1 minus x squared over 1. And here is our final answer for the derivative of sine inverse. So that was a lot. That was like the actual proof, basically, of this. And so we're going to go back, and now we're going to look at the derivatives of basic inverse trig functions. So this is, we just did the first one. We just proved that the derivative of sine inverse of x is 1 over the square root of 1 minus x squared. We just showed that on the last page. So what else do we need? Well, we need the derivative of cosine inverse of x. And while you could go through and do the exact same thing we did here, I'm just going to give you the formula for this. So negative 1 over the square root of 1 minus x squared. If we want to find the derivative of tangent inverse, of x, sorry about that, tangent inverse of x, we are looking at 1 over 1 plus x squared. Those are three main, but we still are curious about the derivative of cosecant inverse, which would be -1 over the absolute value of x times the square root of x squared minus 1, or the derivative of secant inverse secant, which would be 1 over the absolute value of x times the square root of x squared minus 1. And last but not least, the derivative of cotangent inverse. I will move these all in a moment, which is 1 over 1 plus x squared. So let me make those look a little nicer. And if you notice on the side, we have this derivatives of 6 inverse trig functions using the chain rule. Well, this is basically saying if I have the derivative of sine inverse of something other than just x, right? So sine inverse of x squared plus 4 or whatever function in there, it's just the chain rule. So we take the derivative of sine inverse, 1 over the square root of 1 minus x squared, and multiply it by the derivative of the inside thing. Because it's just the chain rule and we know the chain rule and we love the chain rule, I'm not going to rewrite these 6 functions over here as their chain rule versions. We really don't need it. So let's take a moment to find the derivative of the following. Over here, this long method is really just the proof I did on the, like when we started. So I'm gonna say for right now, you can kind of ignore that. So if we want to find the derivative of the inverse sine of 2x, oh man, remember we haven't seen arc for a while. It's the same thing as sine inverse. Well, I know that this is going to be 1 over the square root of 1 minus whatever x is, so in this case 2x squared, and then times the derivative of that inner thing, so times 2, or 2 over the square root of 1 minus 4x squared. I'm really just plugging this into the formula from above. You probably have it on your page clearer or more quickly, so what about inverse tan of 3x? Again, I'm just going to consider the formula. So we're looking at 1 over 1 plus whatever x is squared times the derivative of the inner times 3, or 1 over 1. Oh, sorry. I actually want to make that 3. 3 over 1 plus 9x squared. If you want to pause the video and try the next two, these are a bit more of a challenge, but definitely doable. So pause the video, try C and D, and then you can come back and see how I did them. All right, so for C, we have tangent inverse of the square root of x. Tangent inverse of x to the 1/2. So we're going to use tangent, the tangent derivative, tangent inverse, which if we look over here, the derivative of tangent inverse of some x is equal to 1 over 1 plus x squared. All right, so the derivative here would be 1 over 1 plus whatever that thing was, the square root of x, quantity squared, times the derivative of that inner function, right? The derivative of x to the 1/2, which is 1/2 x to the negative 1/2. Now we just need to simplify this a little bit. So I am going to rewrite this as 1 over 1 plus x times 1 over 2 times the square root of x. And then I guess my last move would really just be to write this as 1 over 2 times the square root of x times 1 plus x. Again, you can distribute. You don't really need to. This is as good as that one needs to be. And for D, we have a double chain rule here. So let's consider the derivative of the outside thing would be 2 times whatever the inside is, secant inverse of e to the 2x, times the derivative of the inside. Okay, so now this is using inverse derivatives, inverse trig derivatives. So the derivative of secant inverse is 1 over the absolute value of whatever x is, e to the 2x, times the square root of whatever x is, e to the 2x squared minus 1. And then we also need to multiply that by the derivative of the inner thing, the derivative of e to the 2x, which would be e to the 2x times 2. So it's actually 1, 2, 3 chain rules, which is kind of a lot. Now let's clean this up as much as we need to. So we really don't need to do a ton, but we can do a little bit at least. Right, we have 2 times 2, which is 4. I know that. I know we have a secant inverse of e to the 2x in the numerator. I have the square root of e to the 4x minus 1 in the denominator. And you're wondering why I didn't put this guy in the denominator or this guy. Well, let's think about it for a second. Any e to whatever power will always be positive, right? E squared is going to be a positive number. E to the negative 2 is just 1 over e squared, not negative. This will always be a positive, always will be positive. So technically, I have an e to the 2x in the numerator and an e to the 2x in the denominator. They are the same, and because it will always be positive, I can technically cancel them. And so I'm really left with just this as my final answer here. Look through the worksheet on this section and let me know if you have any questions.